Last year, astronomers detected a powerful burst of radio waves. Researchers now say the signal came from the defunct Relay 2 satellite, a mysterious radio signal that astronomers initially thought was a fast radio burst, FRB, from far beyond the boundaries of the Milky Way galaxy actually originated from a decades-old NASA satellite called Relay 2. The false FRB was first identified by the Australian Square Kilometre Array Pathfinder (SCAP) radio telescope in June 2024, while the telescope was scanning the southern sky. A notable aspect of the signal was that the radio burst lasted less than 30 nanoseconds, much shorter than most FRBs, but it was so strong that it overwhelmed other signals in the sky. Adam Deller, an astrophysicist at Swinburne University of Technology and a member of the research team, told Space.com this discovery happened completely by accident as we were searching for FRBs originating from distant galaxies. Interestingly, despite FRBs having been known for about 20 years, we still haven't pinpointed their exact origin. However, most credible theories point to a cosmic object called a magnetar, or more specifically, a neutron star with a very strong magnetic field. The Relay 2 satellite was launched into space in 1964 as part of NASA's Relay program. The spacecraft was placed in a medium Earth orbit and was active until 1965, but all of its systems failed by 1967. Clancy W. James, from the Curtin University Radio Astronomy Institute, says of Relay 2, this satellite is a piece of space history as one of the first communications satellites. Not many old satellites remain in orbit, but we're confident this signal didn't come from the satellite itself, as none of its systems could have produced such a nanosecond-scale signal. According to James, at the time the signal was received, the Relay 2 satellite was approximately 4,500 kilometers, 2,800 miles, from Earth. While this distance may seem far, it is very close compared to the typical sources of fast radio bursts, FRBs, which usually originate from distances of up to 9.1 billion light-years. In fact, the closest FRB source identified to date, and the only one seen within our own galaxy, is located about 30,000 light-years away. The initial disappointment stemming from the FRB being a false alarm was offset by the fact that such an accidental discovery was incredibly remarkable. This discovery now presents scientists with a new puzzle. No one yet knows how a defunct satellite like Relay 2 could have sent a signal with such power and characteristics that it could be mistaken for an FRB. Researchers are confident that the detected signal was not an intentional emission, as not only has the Relay 2 satellite been out of service for over 58 years, but it didn't even have the ability to transmit radio pulses this short when it was active. One hypothesis is that the signal was caused by electrostatic discharge (ESD), the buildup of electrical charge that eventually leads to a spark-like jolt. Another hypothesis is that a micrometeoroid may have collided with the satellite precisely at the moment the ESCAP telescope was observing that section of the sky, creating a small cloud of charged plasma. James explained that ESD is essentially the same spark you create when you shuffle your feet across a carpet and shock a friend or enemy. He continued, spacecraft become charged when they pass through ionized gases or plasma in the upper atmosphere, and when that electrical charge builds up enough, it sparks. Newer spacecraft are built with materials to prevent charge buildup, but when Relay 2 was built, that wasn't as well understood. So, it may have just sparked big due to its age. Regarding the micrometeoroid impact hypothesis, James explained that certain predictions suggest these extremely fine particles of cosmic dust, with very little weight, could generate radio waves when they collide with satellites. However, this would require them to be traveling at around 70,000 kilometers per hour. James added, based on an estimate, we think a micrometeoroid with a mass of 22 micrograms could have produced such a spark. However, the problem with the micrometeoroid hypothesis is that, according to existing models, the resulting signal should have lasted on the order of microseconds, not nanoseconds. Furthermore, 22 microgram micrometeoroids are very rare. James and his colleagues estimated that there was only a 1% chance that the ESCAP telescope would have been looking at that part of the sky precisely when such a particle impacted the satellite.